All right, as you can see, we're going to be covering Module 1, Lecture 1 today. And Module 1, Lecture 1 is on problem-solving strategies, and it's a lot different than what most of my lectures will be like, so I don't want this lecture to scare you off. Most of them will be more to the point and be over a specific concept. This one's way more in general, just because of the general nature of problem solving. So let's take a look, and I guess I also want to tell you that this lecture is from Chapter 1, Section 3, so I'll put that up here, 1.3, and the other main section we're covering from this book in Module 1 is Chapter 5, Section 7. And that's what the next lecture will be on, which is on arithmetic and geometric sequences. Now I've got to move because we have 15 minutes for these YouTube lectures, so I don't want to waste any more time. I want to get to the point. To solving strategies, problem solving strategies by George Polya. There's 4 steps. First, read the problem and understand it. Design a plan for solving it. Then carry out that plan. And then when you look back, check your work. Also, he gives some tips. You can draw pictures. You can make lists. You can try guess and check. And then one he didn't give here, we're going to be using algebra to solve some of these today. And then also another tip is to solve an easier problem and look for a pattern. So we're going to try a few of these today, get as many problems in 15 minutes as we can. Here's a real basic first one, and I bet when you read through this you'll decide that drawing a picture is a pretty good idea. Jenny's model train is set up on a circular track. There are 6 telephone poles evenly spaced around the track. I might not get them perfectly evenly spaced, but you'll get the idea. There's 3, 4, 5, 6. Now, it gives you some more information. It says it takes the engine of a train 10 seconds to go from the first pole to the third pole. How long would it take for the engine to go the entire distance around the track? So let's say this is the first pole. We know it takes 10 seconds to go from the first pole to the third pole, so that's 10 seconds. So using some proportional reasoning, it's going to take another 10 to go from here to here, and another 10 seconds to go from here to here. So that's a total of 30 seconds. And drawing a quick little diagram there helped us solve that, and we're pretty confident in that 30-second answer, as long as that train was going the same speed all the way around the track, which I think we're supposed to assume that's going to happen. Alright, now let's look at one where drawing a picture might not help a whole lot, but a systematic list will probably help us. A rectangle has an area of 120 square centimeters. Its length and width are whole numbers, so there's no fractions or decimals. What are the possibilities for the length and the width? Well, here we go. We have a width and we have a length, and the area has to be 120. Well, you guys probably remember, if we talk about a rectangle like this, if you take the width times the length, that gives us the area, and like we said, the area has to be 120 square centimeters. So could we have a 1 by 120 rectangle? In other words, a really skinny rectangle that has a width of 1 but it's really long, length of 120, because 1 times 120 is 120, 2 times 60 is 120, 3 times 40 is 120, 4 times 30 is 120, 5 times 24, let's see, 6 times 20 is 120, 8 times 15 is 120, and we have one more. 10 times 12 is 120. So there's a list with all the possibilities of an area of a rectangle with an area of 120. Now we have to find out which possibility gives the smallest perimeter. Well, perimeter is the distance all the way around this rectangle, from here to here to here to here. Alright, well, I bet you guys agree that means, that means to add up these 2 widths and add up these 2 lengths. So you might remember the formula. The perimeter of a rectangle is 2 times the length plus 2 times the width. And what you do is plug all these numbers in there, and you'll find out, like if I started up here, well, 2 times 120 plus 2 times 1 gives me 242. Whereas if I went way down here on the list, I'd get, I'm kind of out of room here, I'm sorry for the mess, I'll squeeze it in here. The perimeter would be 2 times 12 plus 2 times 10. 2 times 12 is 24, 2 times 10 is 20. That gives me 44. So I'd have a perimeter of 44 centimeters. And you'll find out if you try all of them out that 44 centimeters is the smallest perimeter you can get with those dimensions of an area of 120. So that's an example of using a systematic list and then guessing and checking from there. Okay. Here's another one that's pretty good for guessing and checking. Dan has twice as much money in nickels as he does in quarters. He has 33 coins in all. Well, as soon as you see he has 33 coins in all, we know that the amount of nickels and quarters has to add up to 33. So maybe you try 10 and 23 or 16 and 17 or things that add up to 33. But when you read that he has twice as much money in nickels as he does in quarters, it means he's going to have a bunch of nickels and not many quarters. So within just a matter of seconds or minutes, I bet it wouldn't take you long to finally get that you find out that Dan has 30 nickels, which is $1.50, and 3 quarters is 75 cents, right? And that is twice as much money in nickels as it is in quarters, and yes, that is 33 coins in all. So that's another example of reading the problem, making sense of it, guessing and checking till you get the right answer, and that's one way to do it. Now you could have used algebra on that one, but it was almost quicker just to guess and check probably. Here's one where we're going to, I think I'll save this one for last. Here's one where we're going to use a little bit of algebra. Alright, a local historical society wants to preserve 2 buildings. The total age of the buildings is 320 years old. One building is twice as old as the other. So if I call one of the buildings X, the age of one of the building is X, isn't the age of the older building twice that much? And don't those 2 buildings have to have 321 years between the 2 of them? So by calling the younger building X, I had to call the older building 2X because it's twice as old, and we know the ages of the 2 buildings add up to give us 321. Well, using a little algebra now, 1X plus 2X is 3X. That equals 321, and I bet you remember that the way to solve a problem like this, the way to get rid of a multiplication of 3 is to divide by 3 on both sides of the equation to get that X all by itself. So we get X is 107. So the age of one of the buildings is 107 years old, and the other one is twice that old, so the other one is 214 years old. And that means that when you combine them, when you check it, you find out that that does add up to 321, which it's supposed to. So there's a little bit of algebra. Let's do another one with algebra. Jenny worked 2 part-time jobs. She made $10 an hour driving taxi and $18 per hour cleaning houses. Last week she made a total of $420 and worked 26 hours. Find the amount of hours she spent working each job. Now I know that eventually we could get this using guess and check, because it says they worked 26 hours, right? So you might try 10 hours of one and 16 of the other, or 13 hours of each. But we can quicken the process by using a little algebra. Let's say $10 for driving taxi plus $18 per hour for cleaning houses. So I'm going to use D for driving taxi and C for cleaning houses as my variables. And she made $420. So I hope that makes sense to you, that $10 per hour for driving plus $18 per hour for cleaning has to add up to 420. And then the other equation we know is this: her driving plus her cleaning, the amount of hours has to add up to 26. So there's my 2 equations. Now you might remember way back in algebra, whenever you took algebra 1 or algebra 2, you learned to solve these. These are called systems of equations, and there's different ways to do it. One is to, let's do this. Let's subtract D from both sides. And what I get is I get this C all by itself, so C equals 26 minus D. And since C is 26 minus D, I can put 26 minus D in for that C. That's called substitution. So this top equation now says 10D plus 18. Instead of me writing down C, I'm going to put 26 minus D, because that's 26 minus D equals C, right? Okay, and that has to add up to 420. And the reason we did that is now we have an equation right here that only has one variable in it. It has a D in it. So let's solve this. 10D plus, when I take 18 times 26, I get 468. 468 minus 18D, all I did was take this times this and this times this. That's called distributing. Equals 420. Alright, now let's combine like terms. This 10D minus this 18D is a negative 8D, and I'm going to subtract 468 from both sides. When I take 468 from the left side, it cancels that out, and when I subtract 468 from the right side, I get negative 48. I didn't really have room to show my work. Let me squeeze it in here. I subtracted 468 right here, and that cancels out, and I subtracted 468 here, and that's where my negative 48 came from. Now, to solve that problem, I need to divide by negative 8 on both sides, and when I divide both sides by negative 8, I'm kind of out of room, so I'll come over here. I get D equals positive 6. So that means my driving time was 6 hours, and remember we had 26 hours total. Driving plus cleaning is 26, so my cleaning time was 20 hours. And then, I don't know if you remember George Polya's 4-step is to see is that correct. Well, let's find out if that's correct. $10 an hour driving taxi. So if we did $10 an hour driving taxi, 6 times 10 is 60. And then $18 an hour cleaning. So let's take our 20 hours times $18 an hour. That's $360. And look at 360 plus 60 is $420. So it all checks out. Okay, I think we have time for one more problem. By the way, when you do My Math Lab, you'll see a few like this one right here. Choose any natural number, 1, 2, 3, 4, 5, etc. Okay, let's choose 7. Add 4 to that number, 11. Multiply that sum by 3, that's 33. Subtract 7, we get 26. Decrease the result of step 4 by the triple the original number. Well, our original number was 7. When we triple that, we get 21. So we get 26 minus 21, which gives us 5. Okay, now we're supposed to repeat it. Okay, we're going to repeat it with, let's go to a different color. We'll go to blue. Let's choose another starting number. Let's go 10. Add 4 to it, we get 14. Multiply by 3, we get 42. Subtract 7, we get 35. Now what we're supposed to do is triple our original number. Our original number was 10. We're supposed to take that 35 and subtract triple the original number, which is 30, and we get 5. Well, by now we might say, hey, I think we're going to get 5 every time, and it says use algebra to explain why your statement's true. So let me grab green. Let's use some algebra. Let's say our number we are starting with is x. Add 4 to that number. Well, we get x plus 4. Now multiply that by 3. So we have to take 3 times x plus 4. Well, that gives us 3x plus 12. Subtract 7 from that. Well, when I take 3x plus 12 and subtract 7, that gives me 3x plus 5, because 12 minus 7 is 5. Now we're supposed to take triple our original number, where our original number was x. When I triple that, I get 3x. And I'm supposed to take my 3x plus 5 and subtract 3x from that, and look what happens. 3x into 3x cancels, and look at, I'm going to get 5 every single time, no matter what I start with as my original number. Okay, here's the deal. I went through a lot pretty fast. Just remember, Chapter 1 has a lot on just solving different types of problems, and you're supposed to use these strategies and these tips to solve those problems. And when you listen to my next lecture, that's going to be way more specific. It's going to be learning about arithmetic and geometric sequences. And when you do My Math Lab, you'll see some general problems like this, and then you'll see a lot of problems on the sequences. Bye.